Hi, and welcome to EngPhys 3004 Lecture 5. This is going to be 12.3 Energy Analysis of Steady Flows, renamed to 12.2 in the 5th edition. The 4th edition doesn't actually have a 12.2 really. It's kind of it looks like it's a misprint, at least in my version of the book. Anyway, energy analysis. What we're going to do today is improve on the Bernoulli equation. So to recap, the Bernoulli equation that we derived last time let us pretty quickly get some really easy and kind of interesting results about how flow conditions are changing from one spot to another along a streamline, but it was pretty limited. That was the problem with it. It required a lot of assumptions. Steady flow, negligible viscous effects. It ignored the shear stress on sides, no shaft work, so we're not adding or removing energy with pumps or turbines. It needed incompressible flow, negligible heat transfer or other sources of energy, and again, flow along a streamline. This section, we're going to present a more widely applicable equation and show how it's actually equivalent to the Bernoulli equation if we add some correction factors. This is going to be the energy equation. So just compare them to see where we're headed right now. What we're saying is that rather than these quantities being constant, so equal to their sum at a different point along the streamline, they might be different. And how they're different is if we've added energy with pumps, then we could get higher values, or if we've subtracted energy with turbines or mechanical losses, then we could get lower values. The other difference is this alpha, and this accounts for the fact that the velocity at different points along the cross-section of a pipe can be different. So this allows us to use the average velocity as long as we put in a correction factor that depends on what the velocity profile is. So for laminar flow, it's around 2, and for turbulent flow, about 1.05. All right, let's derive this. It starts with a control volume. We're going to apply the first law of thermodynamics, which is, that's right, energy conservation. So the total amount of energy we're putting into this must equal the total amount of energy we're putting out, we're pulling out of this control volume. Control volume just is a concept for an imagined section of fluid. So we're going to say, let's look at this one amount of fluid, and let's say the volume of this can't change, then that's what the fixed is talking about. We are saying the total energy going in equals the energy going out, and the energy going in is going to be the mass flow rate times the sum of all the kind of total energy per unit mass terms going in. And the energy per unit mass, we're accounting for all the energy here. So now we're looking at H is enthalpy, enthalpy being internal energy plus flow energy, pressure divided by density. And we're going to add to that velocity squared over 2, which when we multiply by the mass flow rate is going to give us the kinetic energy of the entering fluid, plus gz, and m dot times gz is the gravitational potential energy of the entering fluid. So the rate of flow of all of that, rate of entry of enthalpy, rate of entry of kinetic energy, and rate of entry of gravitational potential energy of the fluid coming in. And then we're going to add to that the rate of work, the net rate of work done on this control volume by maybe pumps or turbines. So net input work would be negative if we just have turbines involved. That means we're kind of getting work out. But if there's more pumps than turbines, then we have, or at least more work done by pumps than there is work done on turbines, we'd have this as a positive term. And then there's the net heat flowing in to this thing, net heat entering the control volume. Okay, so that all added up is going to equal the rate of energy leaving, which is the same mass flow rate and enthalpy velocity squared over 2 gz that we had on the inlet side, except now referring to the exiting flow. All right, so if we rearrange this, we can put it in terms of mass flow rate times change in enthalpy, change in velocity squared over 2, g, change in height. It's just a statement of the first law of thermodynamics. Again, energy in equals energy out. Let's rewrite this and see how we can go from this to this term. All right, so what do we need to do? We need to get the gz. It looks like it's pretty much done. We're going to need to, if we compare with that, divide everything by mass flow rate, and that's one of our first steps down here. So we divide by mass flow rate and write it in per unit mass terms. So now it looks something like this, where the Q net in and W shaft net in is per unit mass flow rate, Okay, and the velocity part is pretty much done as well. So what do we need to do? We need to clean up the enthalpy. Enthalpy is internal energy per unit mass plus P divided by rho again. P is the pressure, rho density. So if we substitute that in, we can separate out the internal energy. And now the pressure is looking fine as well, like it should. We've got the net shaft work, and this whole part here, change in internal energy, and the net heat flow is talking about encompassing the mechanical losses. So if we have heat flowing in, but it doesn't account for the increase in the internal energy of the leaving fluid compared to the entering fluid, then there must have been extra energy going into the internal energy that wasn't from the net heat flowing in, which means it came from mechanical losses. So this whole term here encompasses the mechanical losses. This is all the friction, this is the work done, the irrecoverable work of viscous kind of friction effects that are going on. So that will encompass the mechanical losses. This is that's where these terms have gone. That's why we ended up with a mechanical loss term and didn't have any enthalpy or heat terms in what we were dealing with before. So the only thing left to do is to separate out the shaft network into separate terms for work done by pumps and work done on turbines on each side. And we've got basically the adjusted Bernoulli equation with one small caveat. This one assumes that the velocity is uniform all across the inlet or outlet of the control volume. We only have one term for velocity. In reality, we're going to want to deal with flow profiles where the velocity is not uniform. So we need to make some kind of we want to use just one velocity without having to integrate this. And that means we typically want to deal with a correction factor and just use the average velocity. So if we're willing to use average velocity for these, and we have a correction factor on each side that depends on the velocity profile, then we are finally there. We have the energy equation that we are going to use. This correction factor, by the way, called the kinetic energy correction factor. All right, but how do you find these kinetic energy correction factors? Well, what you need them to do is when you substitute in the average velocity for this, you want alpha, v average squared over 2, if multiplied by m dot, the mass flow rate, to give you the kinetic energy flow rate in. So by defining that that's the case, defining that this, using an average velocity, is equal to the actual kinetic energy flow rate, which you can calculate would be rho v cubed over 2 with respect to area over the inlet, you can figure out what the definition of the kinetic energy correction factor is. It's actually like an average over the inlet of velocity cubed divided by the average velocity cubed. Next, we're going to summarize. The energy equation is a modified Bernoulli equation that accounts for non-uniform velocity profiles over inlets and outlets with that alpha, energy added by pumps or removed by turbines with these terms, and mechanical energy lost to heat due to viscous effects from this E-mech loss term. This whole thing is in units of G times Z, which if you think about gravitational acceleration times a height, this is like gravitational potential energy, except without the mass term. So when you multiply this whole thing by mass flow rate, this gives you an energy flow rate, or like a power. In terms of head, you just have to divide the whole thing by G. Now we can talk about the pump head, which is the increased effective kind of like water depth or pressure in terms of water elevation provided by the pump, or the head provided to the turbine, or the head loss from frictional effects, essentially like how much higher we need the water at the start to be because of the losses in the pipes to figure out to get the same flow rate or pressure or whatever we're trying to get at the end of the flow. The book has an amazing picture in it that summarizes the entire energy equation altogether. So the rate of energy flowing in, this big energy here, we can maybe add energy with the pump, although some energy is just lost because the pump is not efficient. That's not accounted for in the energy equation. That's before we do all that. Here's the work rate of the work that the pump is putting in per unit time. So the work rate of the pump, yeah. Useful, U is standing for useful. And then we've got the turbine, the head provided to the turbine. Now, not all of that ends up being energy. Some of it is just mechanical loss in the turbine, and the rest of that gets to be work done on the turbine directly, and finally power out by the turbine. There's all kinds of efficiencies that are lost. There's mechanical efficiency and then electrical efficiency losses that we need to worry about. Now, on the flow side of things, even without pumps and turbines, there's some energy lost just to friction in piping. And that's this term at the bottom, leaving the bottom with this HL, so the head loss from piping. Chapter 14 is mostly about calculating HL for flow in pipes. So given that we've got a whole chapter devoted to that, you can imagine that this is really encompassing a lot of information. In the problems in this chapter, we're basically going to have to tell you information about what it is right at the start, or how to ignore it, and then work with the energy equation. What this also means is that we're going to be working with the energy equation for quite some time, so you definitely want to master the concepts here before proceeding on to chapter 14. As mentioned before, if you get rid of the losses, assume incompressible, and focus along a streamline, you don't have to velocity average, and get back the Bernoulli equation. Now let's look at an example of how we would use the energy equation to solve a problem. This is a hydropower example. Find the head across the turbine, the power delivered to it, and the electrical energy generated by it in this situation. If this was no turbine, no loss, we were trying to use Bernoulli equation, we wouldn't be able to explain why this water has zero velocity, this water has zero velocity. They're both open to atmosphere, and yet there's a difference in elevation of 120 meters. There's no way that Bernoulli equation could be valid with all of those assumptions. So in fact, there is loss in this channel, and there's additional head loss to the turbine. So if we know that 35 meters is lost there, and there's a 120 meter difference there, we just have to subtract them to figure out how much is lost in the turbine. You can write out the full energy equation to see how that works itself out directly. Now, how do we get that into energy? So we mentioned earlier that the head terms in the energy equation, you need to multiply by G and then mass flow rate in order to get that into power. Another way to see that is to say that pressure is H rho G. So that's just our rho GH hydrostatic pressure equivalent type thing. Then we multiply that pressure difference by the area to get a force. And if we multiply that by the velocity flow rate, we get the rate of work done, so the power. All right. So what power is that? That's the power that's delivered to the turbine by the flow. But not all of that becomes electrical power. We need to also consider the turbine's efficiency in generation, and that's this eta turbine gen. We're going to use etas for turbine efficiencies. So what you do is you find the head across the turbine, you convert that to power delivered to the turbine by the flow by multiplying by mass flow rate times G, and then you take into account its efficiency to get to the electrical power generation. This is a combined turbine efficiency. So we sometimes will look at the separate efficiencies going from rotating the turbine itself, so head loss kind of in the turbine, and then once we've got the shaft rotating of the turbine, how do we get from there to actual electrical generation? So there's a place to lose energy here within the turbine, and there's another place to lose energy right there. Here they've encompassed the turbine's head loss with this HL term. Otherwise, we don't have enough information to solve the problem. The last thing that we're going to do today is look at one of the great examples in the textbook. There's a lot more where this came from. Pumping power and frictional heating in a pump. Example 12.5. The pump of a water distribution system is powered by a 15 kilowatt electric motor, shown here with this quality illustration, whose efficiency is 90%. The water flow rate through the pump is 50 liters a second. The diameters of the inlet and outlet pipes are the same, and the elevation difference across the pump is negligible compared to the other numbers involved. If the absolute pressures at the inlet and outlet of the pump are measured to be 100 kilopascals and 300 kilopascals respectively, find out A, the mechanical efficiency of the pump, and B, the temperature rise of the water as it flows through the pump due to mechanical inefficiencies. All right. Now, this efficiency, so first of all, what do we have? We have power the motor is putting in. We have the energy the motor is consuming anyway. That's 15 kilowatts. That tells you how much electrical energy it's using. Its efficiency is 90%. That tells you not the work that the pump is doing on the fluid, but that's just when you multiply these two together, 90% times 15 kilowatts, that's only the work that the motor is doing on the shaft here. So that's the rate of work done on the pump itself by the motor. What we don't know is how much of that actually ends up as mechanical energy in the fluid and how much of it just goes into heat and ends up heating up the fluid. And that's the source of the second question there. So in this case, we do know what the pressure difference is, and that's kind of the result of the pump work. So by looking at the change in energy and the rate of flow, we can figure out the energy flow rate through the pump by the fluid and figure out how much work must have been done on it. So some of it has gone into increasing its mechanical energy by the pressure increasing, but some of it has gone into heat. We can figure all of this out with the energy equation. So the 200 kilopascal pressure difference and the flow rate given, 50 liters a second, tells you the power delivered to the fluid, really the useful power delivered to the fluid of rate of work done on the fluid is volumetric flow rate, delta P, and the motor is using 15 kilowatts of electrical power with this efficiency getting converted by the pump. That tells you how much work is done on the shaft. So the net work going into the fluid is the useful work done by the pump, which is the efficiency of the pump that we don't know, times the rate of work done on the pump by the shaft. Solving for this, substituting in that the work done on the pump useful must be going into the fluid, and dividing out the work that we know was done by the shaft on the pump, we can calculate that the pump efficiency itself is 74%. That's a little bit more reasonable for a pump. Now, we can, from that 74%, determine how much energy didn't go into useful energy in the fluid. That would be the rest of it. So 26% not going into the fluid means that as mechanical energy means that it went into the fluid as heat. Multiplying that by the energy that the shaft was doing on the pump, so the rate of energy the shaft was doing on the pump, in other words, the work, we get 3.51 kilowatts. So that's the rate of heat flowing into the fluid. To figure out how much the temperature changes, we need to use some stuff from 2Ne3 or some thermodynamic stuff here, which is going to be stuff in this course later on once we get to the heat section of it. So don't throw this out just yet. The heat capacity rate given by the product of mass flow rate, m dot, and specific heat, Cp. Let's check out that the units work. We've got change in temperature is heat flow rate divided by heat capacity rate. And heat capacity rate, we've got 1 kilogram per liter multiplied by 50 liters per second multiplied by 4.184 kilojoules per kilogram Kelvin or kilogram degree Celsius. So what are we going to end up with? We've got watts and then joules, but joule per second would be a watt. Liters will cancel. kilograms cancel, degrees Celsius gets flipped back up, and we end up with just a change in temperature. So the heat that has gone into this, even though of all of it's a sizable fraction of the energy that's lost to heat, it makes almost no difference to the temperature of this water. As you know, heat energy is not a very dynamic form of energy compared to kinetic energy.